Hello. Can you hear me? All right. So, hello everybody. See if we can get people to quiet down a little bit. There we go. All right. So, my name is Jason Ekstrand, and I'm going to be talking about how to write a Vulkan driver in 2022. So a little bit about me, for those of you that don't know, most people who I think know me at this point, but if you don't, my name is Jason Ekstrand, JXstrand on IOC. I have been around since about 2013. I started off in the Wayland world, and then I moved over to Intel, where I was working on their 3D driver stack. There I did NER, I did the Intel Vulkan driver, the Spurvita NER parser, ISIL, bunch of other Intel bits. And by the time I left, I was basically the lead Vulkan person. I was also one of their Kronos reps for a while. Then in January this year, I moved over to Collabora, where my new job is basically to do whatever is needed in the upstream graphics stack to make Linux more awesome. So far, most of it has been working on the Vulkan runtime in Mesa and patching things into various drivers, which has put me in PanVK, RadV, Intel. I worked on Raspberry Pi for a few weeks, kind of all over the stack. And so what we're going to be talking about today is a bit about that work and sort of best practices for writing Vulkan drivers in a modern Mesa. So we'll start off with a little bit of history. The Intel Vulkan driver was first merged in April of 2016. We actually started that project in April of 2015, but it had to be behind closed doors because of Kronos NDAs for about 8 to 10 months. And then it took another couple of months to get it merged because we had to do a bunch of upstream refactoring that we couldn't admit to prior to the Vulkan release. And we basically, what that was is moving a bunch of stuff into the source Intel folder because the compiler everything was living in the source Mesa drivers, DRI, blah, 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 blah. Then in October of that year, RadV was merged. RadV started off as Dave took the Mesa code, the AMV code, copied and pasted it into a new folder, changed all the names, deleted all the Intel stuff, and started writing an AMD driver. Every other Vulkan driver in Mesa has basically started this way. Somebody copies and pastes another driver, deletes all of the hardware-specific parts, and starts typing. This has led to quite a bit of sort of copy and paste, and I have been working over the course of the last 2 years to try and remove as much of this as possible. The first significant common component was the Windows system code. When RadV was originally merged, I told Dave that one of the conditions of merging it was to deduplicate Windows system between Intel and AMD because I didn't want both of us writing X11 code wrong differently. And that was what it was. It was wrong in both of them, and it was different. Then in 2020, when the private data extension came out, I started building some common code. Started with a common base object that everybody could use that held all the private data bits. There was nothing hardware specific about that, so I figured, let's go ahead and do that. We also added common entry point table generators. Those were big giant piles of Python that parsed XML and dumped out C code that was copied and pasted from driver to driver. And by that point, it was starting to become a problem because every time we bumped the core Vulkan version, we would have XML format changes that we would then have to replicate across all of the drivers before we could merge the new XML, and it was getting to be a maintenance headache. Then this year, a bunch of stuff has happened. I built a common render pass implementation so that you can implement just dynamic rendering in your driver, and render passes happen by magic. I did some common Vulkan state tracking, which merged, and then I also have some common Vulkan meta code for copy blitz and clears that's sitting in a branch that is hopefully going to land this year sometime. So that's kind of quick history. I did not put all the other Vulkan drivers in there and find dates for them, but there have been a lot of other Vulkan drivers added. We're up to 8 now, I think. 7, 8, something like that. Okay, so this is going to be sort of not really a tutorial, but more of a here's the different pieces and here's how you would go about it if you were doing it from scratch today. So first of all, this is pretty common. This is the basic directory structure. So you have some source/hardware folder. Some people have gone with the actual name of the company, like source AMD, source Intel. Some of them have gone with source Panfrost or source Freudino to use the more open source friendly name. And then in there, you've got your compiler, which is shared with the GL driver. Maybe some other bits, like Intel has an image layout library. They've got some stuff for generating pack headers from XML, and a bunch of other stuff in there. And then you've got your Vulkan directory that contains the actual Vulkan driver. That's the general structure. You don't have to do that. This is a C project. There's nothing enforced. But this is the way that most of them are organized. So starting off, every Vulkan object that you create needs to derive from VK base object. This is the sort of base, if thinking in terms of object-oriented programming, this is the base object that everything needs to derive from. It handles private data. It also, you can use VK-defined handle casts that will define cast functions to get you to and from the VK device or whatever handle name. And a bunch of that stuff is dealt with there, and we also do some like runtime type checking and stuff in there that's handy. You can also derive from other object types, so we have more specific things like VK device, which has some nice stuff for devices in it, and VK image and VKQ, and then those derive from the base struct. So again, it's your standard CS 101 object-oriented programming course. Then the common dispatch framework is where stuff really starts happening for you. So the base requirement is that you have to use VK instance, VK physical device, and VK device. And these contain all of the dispatch tables for actually providing entry points to the application. And they also contain some stuff about enabled extensions, disabled extensions, etc. Everything else still needs to derive from VK base object or something else, but the instance, physical device, and device absolutely have to derive from the base objects. You then use this VK entry points gen script somewhere in your driver directory. You call it from your Mesa, and it will generate entry point tables with driver name prefixed entry points for everything, and then automatically populate. And then it also generates extern tables that you can then hand in when you initialize the objects. And then from there, VK get proc address is implemented for you. Part of the reason for the base objects is that we track enabled extensions, and we automatically deal with all of the nonsense in Vulkan about how if certain extensions aren't enabled, then you have to return null from get proc address, and that whole mess just gets auto-magicked. There's a lot of code gen that makes that happen. So this is sort of the base. Everybody should do this. If you're not doing this, I will knack your driver. But I don't think that there's any problems here anymore. We've all gotten converted. Once you have this, you can also delete all of your VKFoo to VKFoo2 wrappers. So there's piles of places in the spec where we have extended, where we had a version of the function and then we needed to be able to extend it because we whipped out all the extensibility in Vulkan 1.0, which was a mistake. And so there's a bunch of places where we have a thing and a thing two, and there's a few thing threes, but not very many. And so we have all of these common wrappers, and all they do is they implement the old entry point in terms of the new entry point. And usually that just means taking function parameters and shoving them in an extensible struct and then calling it. And so in your driver, what this means is that you should never implement the base version. You should always implement the most recent version that's available in the spec, and we will go in and fill in all the others. And the important thing to know, a bunch of people have missed this, is that you do not need to implement the future-looking extension yet. We will just go ahead and handle that. So even if you haven't implemented, say, copy commands to the extension, you should still implement the 2 version of all the copy commands, because that way you don't have to deal with it later. You don't even have to worry about the rename. This also works for synchronization too, which is a bit more complicated. It added 2 versions of piles of bit fields that are now 64 bits. And there's a bunch of reshuffling that had to happen for that. And most of that is handled for you if you just implement the 2 entry points. So it's very convenient. It gets rid of a lot of boilerplate that we were all retyping. And that's another one is logging. I won't spend a whole lot of time on this. We have log macros. It's in vklog.h. The big thing that this gets you is that it reports to standard error, VKKHR debug utils, and VKK ext debug report. So it reports all of the places, all the things. You just call the logging helpers, and off you go. These also work through, I think they go through the Mesa logging framework. There's a lot of logging frameworks in Mesa, but they plumb through most of the right places. So it will show up in debug tools, and if people are doing captures, it should show up there as well. We've also done some stuff around error reporting. This is pretty standard for people who've been working on Vulkan drivers for a while because we inherited this from the Intel driver. But basically, if you wrap error codes in the VK errorf, it allows you to also provide a message, and this gets logged when the error gets printed with a line number and stuff, so you can easily find where that error came from in the driver. We also recently added support for error handling on command buffer recording. So with command buffers, most of the recording functions return void, not an error code, and you're expected to just set it on the command buffer and keep going. So we have facilities for handling that. Most of the drivers are converted at this point. The Intel driver isn't because it's annoyingly complicated because of some decisions that I made that might not have been the best ones. But I do have an MR somewhere. I just haven't gotten Lionel to review it yet. We also have device loss reporting, which, again, it's the same sort of a thing. Device loss messages are supposed to be sticky, where once you return it, you're supposed to continue returning it. And so there's some helpers to deal with that and also do it in a as thread safe as reasonably possible way. That one's tricky because you can end up with device loss coming from any thread, and then it should theoretically show up on everything eventually. And we should, in theory, handle that propagation now if you use the helpers. And again, I think most of the drivers are converted, but I'm not sure if like the new Imagination one is converted yet or not. Okay, now let's get to the actually interesting stuff. So most of the stuff that I've just talked about is basically boilerplate. We did something clever in one of the drivers, and all the other drivers copied and pasted it. But it wasn't actually that much code. It's mostly a matter of making sure that it's consistent and correct. Synchronization is where things really started to get interesting. And it was mostly okay up until we implemented timeline semaphores. And then the Intel people and the AMD people both implemented them wrong differently. And there was a lot of back and forth, and eventually I just said, I'm done with this. I'm doing synchronization in common code, and we're going to get it right this time. And so the rule of thumb here is that unless you are a very, very magic driver, which currently the only driver that I am allowing to be sufficiently magic is the Venus driver, because they're trying to map Vulkan primitives inside the VM to Vulkan primitives outside the VM, and that's kind of okay. But every other driver goes through the common synchronization framework. And so the moral of the story is do not implement VK. That should be VK fence, not VK event. Do not implement VK fence or VK semaphore yourself. Instead, there's VK sync type, which has like a V pointer table and stuff like that, so you can customize it for what you need. There's a few basic ones that are provided. So there was one that wraps the sync object that's just provided for you. And there's a couple of others that are common. Or if you need to do your own thing, then you can implement it yourself. Like the Intel driver has one that uses a BO as the core synchronization primitive for Windows system integration. But you implement the VK sync primitive, and each VK sync type has a set of features and capabilities on it, and then a set of function pointers that it works with. And it can optionally support all the things. And then the VK fence and VK semaphore are implemented in terms of this. And this allows us to sort of make all that stuff common and reason about it at more of a core level than we were before. Along with this, we have common QSubmit. So the way that this works is that instead of implementing VKQ submit yourself, you implement the VKQ driver submit hook. And this takes a struct that gets passed in as a pointer, and that contains a set of VK syncs that are your weights and a set of VK syncs that are your signals and all your command buffers. And that's what you actually see inside the driver. In the common code, we do a bunch of juggling. We spawn threads behind the client's back if we need to. We handle all of the annoyance around timeline semaphores. We can even potentially handle CPU work that needs to block. So Lava Pipe these days does not carry its own thread pools anymore. It just sets the bit that says I might block on things and then just executes straight inside of its driver submit hook. And we thread behind the client's back and it still looks like a GPU driver. The Raspberry Pi driver is also taking advantage of this because there's a few places where they have to do stuff on the CPU, which they're going to eventually have to get over that. But for now, it is working. And they're taking advantage of that as well. There is a caveat there about sync file export, which I'm not going to go into in detail. And then because we're doing everything in the common code, we can also do the idle handlers. The big win that this gave us was dealing with timeline semaphore support. So with timeline semaphores, we're in this annoying situation where we have this cross-process dance that we have to do in order to linearize the dependency graph so that all of the different kernel submit ioctls in all of the different processes get called in a valid order. Because timeline semaphore allows, from a client perspective, allows you to do wait before signal, where you have one process that waits on a thing and then another process submits the work that's actually going to signal it. And we can't do that in the kernel. And so we have this very careful cross-process dance that ensures that everything gets submitted in the right order. And the kernel primitives have all the bits we need for that. But getting that dance actually correct is really tricky. And that's where both Intel and AMD went wrong for a while. And it took us quite a while to get all the bugs out of it. But at this point, I'm pretty sure we're correct. But that was the big motivation for the common code, is that we've been doing this dance and getting it wrong. And if me and Boss can't figure it out, I have trouble trusting everybody else. So the next big one that is really useful for drivers is render passes. So in the tiler space, render passes potentially provide some benefit because you can like combine things together. You can potentially reorder some things. You can do tile merging. In the immediate mode render space, which is AMD, Intel, NVIDIA, they provide basically no benefit at all except forcing the application to not do copy commands in the middle of their draw. And it kind of forces them to push all the flushes outside of the draw, which is a good thing overall for performance, but that's most of what it gains you. And the whole giant multi-sub-pass thing is just a pile of code that we all have to type. And so when dynamic rendering came out, which dynamic rendering basically reduces all the render pass stuff down to the D312 model, where you still have a render pass that you have to begin and end, and you can't do any copy commands in the middle of it, but you don't have this giant structure that you have to create and pass into pipeline creation and that the application has to manage. And instead of everybody going and implementing two completely different paths in their driver, I went out and built a common render pass implementation that's implemented in terms of dynamic rendering. So right now, Intel and AMD are using it. And Lava Pipe, I think. I don't necessarily expect the tilers to, just because, again, render passes theoretically do provide some value there. But for the immediate mode people, there's no point in having them be a driver-specific thing. So you have to, in order to use it, you have to support dynamic rendering. You have to support a pseudo extension that allows us to do layout transition merging with fast clears, which is pretty important for performance on AMD and Intel potentially. In certain cases, it kind of depends on what's going on, but so that is one sort of extension on top. You have to lower your input attachments, and then you have to provide the feedback loop layout extension, roughly. And then with this, we can implement all of render passes for you in common code, and then you can just drop that whole giant pile. For both RADV and the Intel driver, it ended up being about a net minus 1,500 lines of code. So it's a pretty good code drop, and then we can all just forget about it, and you don't have to think about that inside your driver. Again, you can still implement render passes if you want to, which so far the tilers are doing, although Alyssa and I have been scheming about possibly trying to do something common there, but it's a lot trickier on the tilers if you want decent performance. The other one that's pretty new is graphic state tracking. Currently, nobody is fully using this. Basically, there's a new graphics pipeline state object that scoops up all of the pipeline state into a single object. And it's designed to make it a little easier to work with because you don't have to deal with garbage pointers. There's an annoying bit in the Vulkan spec where the application can provide completely invalid non-null pointers under certain circumstances, and we get rid of that for you. But the bigger thing that it does is it handles all of the sort of state accumulation that you need for pipeline libraries. So pipeline libraries, you can specify basically your pipeline in 4 different chunks. You have a input assembly chunk, you have a pre-rasterization shaders chunk that is all your geometry pipeline, and then you have your fragment shader, and then you have your fragment output chunk, which is basically blending. But you still have like a final pipeline at the end, and this deals with all of the splitting up the state and then helping you recombine it later and handling all of that. And it also deals with like avoiding invalid pointer chasing, and generally it's nicer to work with than the Vulkan structs themselves. It also deals with extensions for you, so instead of having to chase extension structs, the extended stuff is just in there. And if there is a default value for the unextended version, then if the extension isn't present, you get the default value. So you can just read it, and it's like you writing Vulkan 1.0 again. You don't have to deal with extensions or think about that. So it makes things a little bit easier. The biggest thing, though, is it helps with pipeline libraries. The other one that I did was the graphics dynamic state, which provides helpers for doing CPU side tracking of dynamic state. So right now, everybody has a dynamic state struct. They all have implementations of VK, CMD, set, whatever. They all have a set of dirty bits. They all do the tracking themselves. And this is another couple thousand lines of code that everybody is just copying and pasting for absolutely no good reason. So there is now a VK dynamic graphic state struct and helpers to work with it. So you can populate it from a pipeline, and it will take all the dynamic stuff from the pipeline and put it in there. You can copy them around. You can merge them. We do dirty tracking. And then if you use this mechanism, all of the VK CMD set things are implemented for you. You do not need to have those in your driver. You can just delete that giant pile of code. And again, this is another 1,500, 2,000 lines, depending on how many extensions you've implemented. What you see in the driver is there is a bit set of dirty bits basically split up as per the VK CMD set things. And so you just do if this bit is set, or this bit is set, or this bit is set, emit the packet. So far, the Intel driver is the only one that's fully converted over to this that's in the tree. I am hoping the AMD people will convert eventually, but I haven't actually gone out and done the typing for them. And they've got pipeline libraries and other stuff in flight, so I don't want to stomp on that. But it's, yeah, basically everybody has been doing this in the driver, and there's no reason why we all need to be doing it. Originally, when Vulkan was first being designed, the thought was that the CMD set things would actually turn into hardware commands on the spot. But between having to deal with multiple state bits in single packets and doing combining, and having to deal with like meta commands, which need to be able to save and restore, so you have to have a shadow copy anyway, and all the other things you have to do in order to actually build a driver. To my knowledge, the only hardware where it's actually practical to do that is NVIDIA, and only if you're willing to do some other shenanigans. So it's, in practice, it's ended up that everybody has built the dynamic state tracker, and there's no reason why we all have them. The other one that I mentioned briefly at the beginning is meta ops. So Intel does not do any Vulkan meta stuff, but most of the other drivers have gone that direction, where they implement copies and blitz in terms of other Vulkan commands inside the driver, and they just save all the Vulkan API state and then call a bunch of stuff on their command buffers. I've been trying to build something that we can do in common code for that. I've got the core infrastructure, so it can hash and cache pipelines and things and image views and things like that. I've got code to track transient things on the command buffer. So like if you have to create a bunch of image views to do copies, then we can track that on the command buffer and destroy them when the command buffer gets destroyed. And then the save and restore has to be left up to the drivers, because even if you're using the common dynamic stuff, there's still like descriptor sets and other bindings that you need to be able to save and restore. So that's still up to the drivers. But hopefully most of the infrastructure can be made common. So far, what I have done there is I've got clears working. That probably needs some reshuffling, but I've got most of the stuff needed for that, including a mechanism for allowing, I haven't actually hooked this up in any drivers, but in theory, a mechanism for allowing drivers to use their own custom rectangle primitives instead of triangles if they want to, and deleting the geometry part of the pipeline if they want to, or in the case of tilers, potentially even doing it as a load op. But it needs to be prototyped in more drivers before I'll be convinced that I've gotten it all right. I've got code for Blitz. The next one I'm probably going to be working on is resolves, because I'm going to need that. And then copies haven't been touched. I have been testing. I originally tested by hacking up the Intel driver. I'm now pretty heavily testing things in NVK. And then Alyssa and I have been scheming a little bit to convert PAMVK, but neither one of us has worked up the will to actually dig into it. I'm hopeful that this will eventually sort of replace all the driver custom stuff, at least where we can. The custom should still be able to be done. In fact, I'm hopeful that the custom stuff and this won't actually conflict at all, and this will actually be helpful for that, where you can just sort of reuse like the hash and cache that I've built. But that's going to be up to drivers how they want to do that. I know AMD currently is able to compile all of their pipelines that they will ever use at driver boot. That's not practical with this because there's just too many combinations, because we have to stick actual formats and things. But hopefully at least some of the framework will be useful for that, and we can start trimming down some of the driver custom stuff. Okay, so that's most of the stuff I've been doing in the Common Core. Now time for the fun part of my talk. So I called my talk How to Write a Vulkan Driver in 2022, and we've been keeping it kind of quiet, but if you didn't know already, I have actually written a Vulkan driver in 2022. It's called NVK. I have a shirt. I have stickers. You can all get stickers. Just talk to me, Mark. We have stickers. And it is a brand new from scratch Vulkan driver for NVIDIA hardware. So it's been mostly done by me and Carol Herbst and Dave Early at Red Hat. Dave kind of got us started with some compute support. Carol has done a bunch of miscellaneous things, and then I've been kind of architecting the core of it and filling it out. Unlike most other Vulkan drivers, I started this one from blank files. So we have not been copying and pasting very much from other Vulkan drivers. We have not been copying and pasting from Nouveau for the most part. We are using the newly released official NVIDIA headers. So about 3 or 4 months ago, NVIDIA dropped the source code for their kernel driver. They've also started dropping official headers. And we are using those instead of the reverse engineered Nouveau headers, which has been really nice because now we actually know what all of those unknown packets are, or at least names of them, which is pretty cool. And my goal for it is for it to eventually become the RADV of NVIDIA hardware, and also to eventually become sort of the new reference driver. Most of the drivers in Mesa have started by copying and pasting from either Intel or RADV. I am hoping that, I don't know if there's any more hardware to write a driver for, but I'm hopeful that this will become sort of the new one that people copy and paste from. So with that in mind, I have been trying to keep things as clean and well organized as possible. I have been taking full advantage of all of the nifty runtime things. There is no legacy in there anywhere. It's actually a pretty clean code base right now. I know that's not going to last. I'm well aware. I've been an engineer for a while. But at least right now, we have a clean code base. Current status. So I have been developing on Turing. I've got a 2060 in my box. Carol and Dave have played around with Amper a little bit. But so far, the current official support is Turing Plus. Carol has patches for getting us part of the way there on Kepler. And later, and it worked, and it had reasonable CTS pass rates until I went in and made absolutely everything in the driver rely on the MME, and now it doesn't work at all. But hopefully somebody can come in and backfill some of that. The biggest blocker is that we're going to need a new kernel API. And we're pretty thoroughly rewriting a lot of the Nouveau stack in this process. But part of it is that we need a new kernel API because the current one is very old school. And we really need something that allows us to do particularly separate binding and submission, because in order to properly implement Vulkan on NVIDIA, we absolutely have to be able to do sparse binding, because you have to be able to put information about depth buffers in the page table, which is really annoying. And that just doesn't work with Vulkan's sub-allocation model unless you can control the page tables from user space. And so that means a pretty substantial surgery to the Nouveau kernel driver. Dave has started working on some of that. Ben might be doing some of that. I have told people that I really badly do not want to do any of that. I don't want to end up as a kernel maintainer. But that is kind of the big blocker, and it's probably going to be blocking getting NVK merged if we can wait that long. Just because I really, really, really do not want to be supporting the old Nouveau kernel API for the next 10 years. I would much rather just get it fixed and get everything landed and deal with the bugs than having to support the old legacy API forever. It's good enough for bring up. We are at about a 98% CTS pass rate with a very basic feature set. There's no tessellation shaders. There's no geometry shaders. There's piles and piles of features that aren't implemented. We're at roughly 20 to 25% of what I would expect to be a final pass rate for a competent driver these days. But we are getting there. If people want to test and contribute, it is living in the NVK/main branch in Nouveau/Mesa. There are merge requests. We've already gotten some merge requests out from people who are not me, Carol, and Dave. So feel free to help out. There's lots and lots of little features that need to be done. There's probably lots of bugs to fix. The biggest request is to be nice to us with the issue tracker. Don't file with issues for every single feature that you want to see in the driver. We know that it's missing all the features. We don't need piles of issues to know that. Also, please don't file games bugs yet, because again, we know there are lots of missing features, which means if your game is running on something like DXVK, it's probably taking very, very bad paths, and we will deal with that once we're actually up to speed and taking the proper paths. But so yeah, but feel free to help out if you want. Feel free to play around with it. I did get Windows System Integration hooked up this last week, so it will actually draw things on the screen now. That's kind of an important feature, but not actually that important for development, just important for users. Mark is sitting over there with his finger on the button. There's going to be a blog post coming out with more information on the Collabor website, and it will be advertised on Collabor Twitter and my Twitter as well. So with that, thank you, and I will take questions. And also, Collabor is hiring, so. I don't think that mic is working. I can hear you and I'll repeat it, so.
Basically, all I wanted to say is I've been helping with our reviewing all of Ben's work for getting both the GSP loaded and also the API actually working so that we can actually get all that done. So it is a work in progress. It's definitely happening.
Yeah, so that was Lude, I think, am I pronouncing that right? Yep. Saying that she is working on helping Ben get everything reviewed for new API and GSP firmware, which is hopefully also going to get us reclocking. Cross your fingers. Any other questions? Just ask up and I'll repeat it.
Did you find that the official headers have useful information in them? Like, is it just names or not?
So the question is if the headers have useful information, or is it just names? It is mostly just names, but it's also it's not just register names, it's also field names. And so everything is broken down to, this particular value in this particular register. And that has been really helpful. It's not documentation, but it is a lot better than what we had before, which was a bunch of people guessing what things were called based off of what other drivers poked into them. And so there have been a number of places where it's, oh, so that's what value we're setting there. Because like with Nouveau, there was also a bunch of unknown headers, just UNK and then the address number for the register. And it was set to magic value, and nobody has any idea what that magic value does. And now we can actually see, oh, that's controlling caches. Oh, that's controlling this bit over here. And so it has been very helpful to have that information. Again, it's not complete, but it is helpful. The other thing that it gives us is it tells us stuff that we're missing, because like as people enable hardware, sometimes they miss registers or there's features that we don't know how to hook up. And this gives us, they're not complete. There is stuff that is scrubbed out of them, but it does tell us about stuff that we were missing. Like, here's a depth test register over here that nobody knew about that we should probably be setting to a reasonable value. And the way NVIDIA hardware is designed, it's generally pretty close to the API. And so between the names and good API specs, we can pretty much figure out what most stuff does. So it's a lot better situation than we were in before, but it's not quite giant PDFs describing everything.
This is
Josh.
maybe more to the NVIDIA, not Nouveau kernel people. But was there anything interesting in the NVIDIA kernel release that would be useful for Nouveau?
So the question was there anything interesting in the NVIDIA kernel release that would be useful for Nouveau? And I think, yeah, I haven't been working on it, but I'm pretty sure it's pretty much a gold mine in terms of figuring out how to properly program the hardware, because kernel is a lot trickier than user space, because you don't have this giant API that basically one-to-one maps to the hardware that you can look at for how things work. You're flying blind if you don't have documentation, and this at least tells us what's going on and how do they load the firmware, and then we can try to reverse it out. But so I think that has been very helpful, and I think they've already fixed a bunch of bugs based off of it as well. So yeah, it's been useful. Again, it would be awesome if they gave us actual PDF docs, but short of that, this is a lot better situation than we were in a year ago.
Yeah, so we have some questions from people attending online. From Immersion, what would be a good first task to start contributing to NVK?
So good first tasks. There's a lot of stuff in there that is basically like maybe even already hooked up. We just haven't advertised the feature bit or the extension name, and it just or there's maybe like one bit to set somewhere in the hardware. There's a lot of those features. So where I would like to see people start is just sort of going through the Zinc checklist, because to me that's the next thing to get up and running, is to try and see if we can get all the stupid little features that Zinc needs. They're not stupid, they're tiny. And they seem a little bit silly, but like there's a lot of features that are needed in order to get that up and going at full speed. And that seems like the next sort of milestone to be able to do, is to see if we can get a bunch of that running, because that will also pick up a bunch of what DXVK needs. But generally, all the extensions, like we should be able to eventually implement all the things. It's just a matter of one by one turning things on and running the CTS tests and making sure they work.
Another question from people attending online. Plans for more common code besides Meta?
Plans for more common code. Most of the common stuff has been driven by need, and right now I'm not aware of anything else that's a big problem. We do keep finding little things, like the command buffer error tracking. We also did command buffer state tracking. I don't remember if that one's been merged yet or not. But it's mostly based on need. The big blocks, I think, are what I listed. But as time goes on, we will probably see more and more things, particularly as Vulkan evolves. a lot of what we're doing in the common code is allowing your driver to sort of stay at the bleeding edge and not have to worry about all the trailing stuff behind the bleeding edge. And so that's where like the synchronization 2 port comes in. That's where render passes come in. And so that's going to depend on what happens in Vulkan as a whole, what new stuff comes up. It's a really bad example, but if we decided to implement the rest of the geometry pipeline in terms of mesh shaders, which I actually don't think is a good idea for a number of reasons, that would be something we might attempt. But again, we're not going to do that. That's just an example of new thing, old thing, and doing the mapping. But again, we do that based on whether or not it makes sense, not trying to do all of it, because sometimes it doesn't make sense for performance. But the render passes was one case where it definitely did make sense. But yeah, again, it's being driven by what do people find that's duplicated and where does Vulkan evolve, and I can't really predict that at this point. Okay, so the question was, why are we not using the open source NVIDIA driver? And the short answer is that it's not really in a shape that can be upstreamed. The API is completely unstable. It can potentially change at any moment. It's all based on user space submission directly into firmware, which means that if the firmware changes, again, that's not stable. It doesn't really integrate with the rest of DRM because it's designed to be built across dozens and dozens of kernel versions, including kernels that are not Linux. So it's generally not something that we want to drop into upstream in its current form. And it's, I think, questionable whether retrofitting that is actually easier than retrofitting what we have, or even possibly replacing what we have. Boss. Am I going to rewrite the compiler too? Yes, I did not put that on the slide, but that's my next project. So I got a big clap from Martin in the back. So yeah, the whole Nouveau stack is kind of in the same state where it was state of the art a decade ago when it was first written. And there have been a lot of amazing people that have worked on it over the years. It's just not had the manpower to actually stay up to date. And so it's fallen into disrepair as hardware has been enabled in the fastest and cheapest way possible, and people are just trying to stay on top of it and keep afloat. And so the compiler has had the same problems where it's, was state of the art at the time, but these days it's getting pretty crufty. And so, yeah, my next project is the compiler. I'm actually going to be sort of stepping away from the main driver portion, and I'll still be reviewing stuff. I'll still be helping stuff land. Maybe even get a minion to work on some stuff at Collabora. We'll see. But the my focus is going to shift towards the compiler, and my plan is to start from blank files again and pull stuff from the old compiler as needed. But we'll see where that goes. I think that's probably going to be the solution. Is it's just going to get wholesale replaced. Because along with being sort of old and patched onto, it's also it thinks in terms of TGSI in a lot of ways. And slowly refactoring and trying to avoid breaking Nouveau is probably more work than just opening blank files and typing at this point. So I'm also hoping that it's going to be a best practices thing as well, where I'm hoping to do all of the neat things like SSA register allocation and all of those good things, but we will see how that goes. NVIDIA hardware is actually pretty darn compiler friendly, so I've got high hopes. Upstream merge request when? As I said, I do not want to merge a driver that supports the current Nouveau kernel API. I can post a merge request and leave it as draft status if people think that that's a nice way to find it. But it's probably going to sit there as a draft for the next 4 or 6 months, however long it takes to get the kernel API in shape. Because yeah, I don't want to. Again, it's not that we can't do any Vulkan. Getting Vulkan actually conformant on the kernel API may not be practical without real nasty hacks. And I definitely don't want to support it for the next 10 years. So I don't want to merge those files. But once the GNU kernel API is in shape, yeah, we're going to post the merge request, and that will be the user space driven that drives merging the kernel changes, and then we'll land it as soon as that's in shape. So hopefully we'll get it in upstream in 4 to 6 months is probably the quickest that I could guess, but it's going to depend on how quickly all the Red Hat folks are able to get the kernel in place. Other questions? Chad?
Comment. I work on the magic driver, Venus, and all those common helpers, I'm so jealous of. That's all.
Yeah, that was Chad who works on Venus some, and he's jealous of all of our common helpers. Although, we'll see. We might be able to start using more of them. Hopefully.
So I'm just wondering about having state helpers, and curious how much overhead do we add?
So Timur is asking how much overhead the graphic state helpers add, and the answer is that I have not solidly benchmarked it. They are more complicated than the ones we had in Intel because they actually check for whether or not the state changes before setting the dirty bits, which costs you more in VKCMD set, but may save you in other places. And so it's kind of hard to know whether or not that's actually a win. It does mean, particularly for pipelines, that we aren't resetting every single state when pipelines change. We only set the delta, which from the perspective of shorter command buffers and less PCI traffic and less hardware time being spent parsing those command buffers, it's going to be a win on the GPU. Whether or not the check for whether the state changed is on the CPU is going to balance that out, I don't know. I do not have numbers on that. I would love it if somebody got some numbers. Boss.
I think we just removed a bunch of the comparison.
Sorry, I'm having trouble hearing that.
I think we just removed a bunch of those compare in recipe based on X benchmarks.
Like VK overhead.
Okay, yeah, Boss is saying that they removed a bunch of the comparisons on RADV due to the benchmarks. And it could be that that's better. Part of it also depends on the hardware because RADV is pretty close to packet for packet in terms of VKCMD set maps to this packet over here. On hardware like Intel or ARM, where that's not the case, and you are recombining for absolutely everything, I think the balance very well may shift. So it's not clear to me that there's a clear answer for everybody, which is unfortunate, because if we're going to do stuff in common code, we have to pick one. If it really is important for ADV to do them themselves, then they can do them themselves. There's no requirement there. It just means that, the meta stuff gets more complicated.
Is there room there for custom state bits?
Timur is asking if there's room for custom state bits. I don't see why not. There aren't any currently because, again, it's been based off of what the API provides. And with Dynamic State 3, that is now basically all of the things. But if you have some bit of state that gets derived in the pipeline and you want to pass it through there, I don't see why we couldn't. It's just an enum that we use to index bits in a bit field, so there's very little overhead to adding one. We're currently at 64 bits of bit field. If we go over that to 96, it might add some overhead somewhere, depending on stuff and how well the compiler optimizes, but I don't see why that would necessarily be a problem if somebody needed a driver-specific bit. And Arik is tapping his watch, so I think we need to wrap it up. So thank you, everybody, and come talk to me or Mark over there, and you can get an NVK sticker. I've got like 300 of them to hand out, so, and yeah, thanks for listening.